Hello and welcome to a Maths with Harry lesson. In this video we're going to be having a look at modelling with quadratics. Before we get into any examples or any explanations, we need to know, what does modelling actually mean? I've kind of summarised it into two bullet points, if you like. Modelling, and especially with quadratics, is where we take the quadratic and we apply it to a real life situation. We don't just do maths for the sake of doing maths. Some people might, some people enjoy it, but what we do is we use maths in the real world. And many people with different jobs and things, you can go obviously down many paths, but modelling with quadratics is really useful. It comes under mechanics, if you like, and the examples that I've got in here are quite mechanics-like, but we're going to be looking at it from a pure maths perspective. And we kind of model things like throwing a ball. I'll explain that in a minute. We maybe have a look at, I don't know, throwing not just a ball, throwing something else, a frisbee maybe. We have a look at modelling there, and quadratics comes under modelling, okay? So, real life situations. If we have got quadratic functions, they usually model something called projectile motion. And I'm going to explain this through this diagram here. So here I am. It's not the best drawing of me that someone's ever done, but it doesn't matter, I'm no artist. I'm here and I've got myself a ball, okay? And I'm going to throw this ball. I'm stood on some nice grass. It's a flat surface. We will write that here, flat surface, and this is me. This is the ball, and I'm going to throw that ball so that I'm going to duplicate the ball here. I throw it and it lands there, okay? Now, if I track out the path of the ball, okay, if I just take that ball again, if I track out the path that the ball makes when I throw it like that, what I'm going to get is, and just checking I'm on the right pen, I'm going to get a quadratic that looks like that, okay? That is the path of the ball. And this is us mapping, or modelling, sorry, with quadratics, okay? We've taken a real life situation. Here's me with me throwing a ball, and we've thrown the ball and we've got this path. Every time you throw a ball, your ball is making a quadratic curve. It's following projectile motion. Okay, so every time you throw a ball and it lands on the floor, the path of that ball you can model as a quadratic equation. Okay, it's a parabola. And in the last video, or the previous video, we looked at what a parabola is. It's just another word for a quadratic. It's the shape that the quadratic makes. Okay? So, that's a real life situation. Let's have a look at an example. You can pause this and read it for yourself, or we can read it together. It says, a ball is thrown over level ground from the top of a tower. Okay? The height in metres of the ball above the ground after t seconds is modelled by the function h of t. Okay, we've got this function here. Now, usually with questions like this, we do have decimals as our constants and coefficients, but it really doesn't matter. It's still a quadratic equation. We've got t squared here, we've got t, and we've got a constant. So it's a quadratic, and we're modelling with a quadratic because we're putting it in a real life situation. So we've got the quadratic 12.25 or 12.25 plus 14.7t minus 4.9t squared, and t is greater than or equal to 0. That's quite an important information because t is seconds. We can't have negative time, so it's taken that t is greater than or equal to 0. Part A, what we need to do is we need to find the meaning of, or well, what is, it's asking us. It's not asking us to find anything, it's asking us just to state this. What is the meaning of, 12.25 in our function? Okay, so we can kind of just write that down, have a little think and write an answer down. Part B says, after how many seconds After how many seconds does the ball hit the ground? Part C then says write h of t in this form. For sum A, B and C, we need to find what A, B and C are. And then part D says, using part C, find the maximum height of the ball and the time this maximum is reached. So, press pause and have a go if you want to have a go at it. You might notice what this form is, so you might be able to have a go at part C. You also might be able to have a go at part A. I don't know, but press pause and have a go, and then when you're ready for the answer, press play and we will work through it. Okay, hopefully you've had a go. Don't worry if you didn't, let's work through it now. So, part A. Let's do our answers down here. What is the meaning of 12.25 in this quadratic here? Well, let's think about where we are. We're on the top of a tower because that's where we're throwing the ball. We might not be at the top of the tower, we might just be modelling the ball at the top, okay? But the ball is at the top of the tower and we're throwing it over level ground from the top of that tower. So when we have not thrown the ball, we haven't started the path of the ball yet. So we're at time t equals 0. Okay, we're at 0 seconds. We've not thrown the ball, it's not left our hands yet, we're still at the top of the tower. Now if we think about this equation here, when t is equal to 0, because it can be, it's either equal to 0 or greater than 0. When it's equal to 0, the only term that's going to survive is the 12.25. Because that term's going to disappear because it's got a t in it, so we're going to multiply by 0, and that term is also going to disappear. So the only term that we're left with is the 12.25. So that's going to be quite useful for answering this question. And that is at time t equals 0, we just get 12.25, so that must be the height of the tower that the ball, or the person, I don't know whether a person's throwing it, but the ball is on. It's the height of the tower, okay? So 12.25 is the height of the tower, okay? And it says in the book here, the tower is 12.25 metres tall. And I'm not sure where they got metres from. Oh, it does say the height in metres. Okay, so we can say 12.25 is the height of the tower in metres. Okay, it's always useful to take a unit from the question if you can do that. Okay, so think about the relation of what we're being asked and what's in the equation, and we can see, well, to get what we need, t must be equal to 0. We haven't set the path of the ball off yet, so it must be the initial height of the tower. Okay, after how many seconds does the ball hit the ground is what part B is asking us to work out. Okay, well, the height of the, if you look here, the height of the ball above the ground, this is the function, that's how we're modelling it. When it hits the floor, the height is 0 because we are on the floor, okay? So the height in metres of the ball above the ground will be 0 when we hit the floor. So all we need to do is we need to solve, and I just need to write that down, we just need to solve that equation equal to 0. Okay, I'm just going to solve that equation equal to 0. And to do that, I'm actually going to write it the other way around. So I'm going to put my t squared first, and then my t term, and then 12.25 my constant. Okay, and now all I need to do is I just need to solve that above equation. Okay, and to do that, I'm going to use the quadratic formula. Whenever you've got decimals like this, it's probably best to use the quadratic formula. So my A value will be minus 4.9, my B will be 14.7, and C will be 12.25. And I'll just highlight where they came from there, and I'll highlight that in a different colour. We'll go with red, hopefully you can still see that, and the green there is from the constant. Okay, so now I'm just going to substitute in. So I'm going to have x will be equal to negative b plus or minus the square root of b squared, 14.7 squared, minus 4 times a times c. And I'm going to divide that by, let's just make that a straight line, divide that, I don't think it's going to go, there we go, divide that by 2 times a, which is minus 4.9. Okay, so that's what we should get there. Then all we need to do now is kind of play a game of simplification. I'm going to put ... here because I'm going to jump a few steps. You can work that out if you want to, but I'm going to jump straight to what we get, and I'm going to take this from the solution. Once we simplify under the square root here and simplify our denominator there, we get this. We get minus 14.7 from the term out the front. Then we get plus or minus the square root, and then what's inside the square root becomes 456.19. Okay, so we actually don't really need that square root to be so big. Okay, so the square root of that, and then divided by 2 times minus 4.9, which is minus 9.8. Okay, so then all we need to do is, well, we need to solve that. I can just put that into my calculator. We would probably get this in a calculator paper, okay? So we just need to substitute that into a calculator. And when we do that, that tells me, and I'll put a little arrow here, that x will either be equal to minus 0. Oh, and actually it's t here, isn't it? So I'm just going to change that to t. That's just out of habit. We'll change that to t. Okay, so t is equal to. And the reason it's t, sorry, is because of those there. Okay. All right, so we get t being equal to minus 0.679, and that's going to carry on. We'll just write the first 3 decimal places. Or, because we've got plus or minus here, we're going to have 2 values for t. T being equal to 3.68, and we'll write that to 3 significant figures there. Okay. So those are my 2 values for t. Now, what it said is, after how many seconds does the ball hit the ground? We're not going to have 2 values for t. We need to reject one of the values for t. And to do that, we're going to use this piece of information here. Okay? We've got 2 values for t. One of them is negative, one of them is positive. Now remember, t is time. T is in seconds. So we cannot have negative seconds. And so we are going to reject this value for t, because t is greater than or equal to 0. So we can say then, and so the ball hits the ground after 3.68 seconds. And that is to 3 significant figures. Okay, so that is your final answer to part B. All right, we worked out what we needed to do. We worked out what our A, B and C values was. We set it equal to 0 because we want it when it hits the ground. And this quadratic models the path of the ball. So equal to 0 means we've hit the ground. We've got no height above the ground. We solved it. I solved it for x, but remember, we need to solve it for the variable that we're in. So solve it for t, and then reject the negative t because t is time. Okay, let's have a look at part C. All we need to do is complete the square. Okay, so let's have a go at completing the square. I know I need to complete the square because I recognise that form, and the more of these questions you do, whenever you ask to get it like this, you need to complete the square. Okay, so let's write down what the quadratic was, and I'll write it down from the book. It is minus 4.9t squared plus 14.7t plus 12.25 is equal to 0. Okay, so completing the square. The first thing I'm going to do is factorise out minus 4.9 from the first two terms. When I do that, I will factorise that out. I will get t squared, and I will get minus 3t, and then I'm going to add 12.25. Okay, I don't really need equal to 0 here because I'm just completing the square, so we can have an equals there. Alright, so that's what I get when I factorise out minus 4.9, and then I'm going to complete the square on that inside bracket there. Okay, so I'll have minus 4.9 out the front, and then I'm going to complete the square on that. So I'll have t minus, well, half of 3, which is 1.5. We will square that, then we'll take off what we get when we square 1.5, which is a minus, 2.25. Close the bracket, because now we've completed the square on what's inside, and then I need to add 12.25 to the end. Okay, so that's what we get there. And then all I need to do is just bring that in the form that I want. I'm just going to copy down the form that I want it in. I want it like that. Okay, that's the form that I want. So I'm going to then distribute the minus 4.9 to give me that. And then minus 4.9 multiplied by the minus 2.25 is going to give me this. I'm going to read it out of the book. 11.025. Okay, and then I'm going to just add the 12.25 in there. Then what I can do is, well, I can highlight this in the grey. I can merge those two terms together there to give me minus 4.9 times t minus 1.5 squared. And then when we add those two terms together, I'll get 23.275. Okay, we're very nearly in the form that we want. We've just written our constant first, so I'm going to switch that round. So 23.275 minus 4.9 times t minus 1.5 squared. And then I can say, and so I can state that A is 23.275 and that B is minus 4.9 and C is, B is plus, that's not changing, plus 4.9 and C is 1.5 because they're already negatives there. Okay, and that is our final answer, so we'll highlight that. And we'll highlight that as well because that's what we were asked to do. Okay, so we've now completed the square on our quadratic. Okay, so that really wasn't a modelling question, that was more of just a maths question. But now in part D, we need to apply our answer. So it says, using part C, find the maximum height of the ball and the time this maximum is reached. In other words, find the turning point. We have got, on our quadratic, a negative value of t squared. Okay, our A is negative. So we're going to get the quadratic looking like that. Okay, and then if we had some axes, I don't know where this lies on the axes, but let's say, I don't know, it looks something like that. This value here, this is the maximum. We cannot get any higher. So what we need to do is we need to find the turning point because it asks us to find the maximum height of the ball and the time that that is reached. So, turning point, well, we've just completed the square, so that's why it tells us to use part C. We've completed the square, and so all I can do is just take the turning point straight from completed square form. I'm going to write TP for turning point. The turning point will be, well, if we look at it in this form, I'll highlight it in grey, you might be used to taking the turning point from that form with our squared function first and then our constant. We're going to take the opposite side of this number to be our x value, or in this case our t value, 1.5, and then take our constant for our y value, 23.275. That's our turning point, okay? Now remember, we've got t values, so I'll write that like that. And our function, well, the y was h of t. And h of t is the height in metres of the ball above the ground. So we'll write that there. So that's kind of the form of our quadratic, okay? Or the form of our coordinates. So what we need to think about here is, well, we're being asked for the maximum height of the ball. We've found the turning point, and so that must be the maximum height of the ball. So we can say max height will be 23.275 metres, and, well, look, it matches up with our value of t of 1.5, and that's reached at 1.5 seconds, okay? And we've worked out everything that we need to work out there because we've been asked for the maximum height and the time that that is reached. So the maximum height is 23.275 and it's reached at 1.5 seconds. Okay, so let's have a look at another example. You can pause the video and have a go, and then press play and we will work through the answer. Okay, example 2 says, well, we've got a car manufacturer and they uses a model to predict fuel consumption, okay? The fuel consumption is y miles per gallon and it's for a specific model of car travelling at the speed of x miles per hour. The y, which is our fuel consumption, is modelled using this quadratic. Part A says use the model to find two speeds at which the car has a fuel consumption of 32.5. So I'm going to go straight ahead and start working on A, because we just then need to work out what that is and then we'll have a go at B. Okay? So a fuel consumption, the fuel consumption is modelled by this quadratic, okay? And the fuel consumption is y. So we want to know the two speeds. Speeds are x, so the two values of x that set this quadratic equal to 32.5. Okay, I have done this answer, so I'm going to have the answer in front of me. So, minus 0.01x squared plus 0.975x plus 16 is going to be equal to 32.5 for part A, okay, because the fuel consumption is 32.5. So what I'm going to do is I'm going to solve this, and again I'm going to solve using the quadratic formula. Okay, so solve using quadratic formula. Alright, so when we do that, what we are going to get is, we will write in red, A is equal to minus 0.01, B is equal to 0.975, and C is, well, what are we going to need to do first before we work out our value of C, okay? We need to get our quadratic equal to 0. So our C value is going to be minus 16.5, because what that tells us is, and I'll just duplicate that there, those two terms, if we minus 32.5 from both sides, we will get that, okay, equal to 0. And then that's where that value of C comes from. Okay, so substituting into the quadratic formula, I'm going to have x is equal to negative b plus or minus the square root of b squared minus 4 times a times c divided by 2 times a. Okay, so that's what we get. Oh, sorry, a is minus 0.01. There we go. Okay, so that's what we get. Now, when you put that into a calculator, you can actually just put that straight into a calculator, and that's what I've done. So I can say ... there's some solutions or method between that. We're going to get two values for x. We're going to get x is equal to 21.7951, and that carries on. And that is when we use the positive square root. Or we're going to have x being equal to 75.7048 ... that carries on, and that is for the negative square root there. Okay, now all we've done is just solve the quadratic when it's equal to 32.5, got two values for x, and remember x is the speed, and so that's our answer. Okay, it doesn't tell us to give our answer to any decimal place or anything, so I'm going to give it to 3 significant figures, and so we can say the two speeds are, and we can say 21.8 miles per hour and 75.7 miles per hour to 3 significant figures. Okay, and those two values, or those two speeds there, are our final answer. Alright, last part of this question, we are nearly there. Part B said find the speed, so find the value of x at which the car has the greatest fuel efficiency. So we need to think, well, how on earth am I going to work out the greatest fuel efficiency? Well, the greatest fuel efficiency is the greatest value of y. And so what I need to do is I need to complete the square, just like in the other example. Apart from here, we weren't told we need to complete the square. So we need to imply that from the question. So what I'm going to do is I'll write part B, and I'm going to just take my quadratic there, and we'll copy that, and we'll paste it down here. So that is going to be equal to 0. And then I'm going to complete the square on that. So I'm going to do a similar method. I'm going to take out, and I'm going to do it quite quickly. We don't need it to be equal to 0 here. I'm going to do this quite quickly. So take out a factor of minus 0.01 from the first two terms to give me that. Okay, and you would probably need a calculator for this. Then what we're going to do is we're going to complete the square on this bit inside, and I'll work across here. That will give me this minus 0.01. Completing the square on the inside, I'm going to have x. I'm going to half the number in the bracket, square that, and take away what I get when I square this number. Okay, so square 195 and square the 4, and then take that away. And then close the bracket and add on 16. Okay, then I can re-expand the bracket if you like. I will have minus 0.01 times x minus 195 over 4 all squared. And then I need to do, well, I've done that, I need to do that now, okay? And when I multiply the minus 0.01 with this, what I will get is, and these numbers should be correct, I should get 1,521 over 64 plus 16, okay? And then I can add those two terms together there. And when I do that, I will get this minus 0.01 times x minus 195 over 4 squared. And if we add those together, I should get 2,545 over 64. And we can just double check that on a calculator, just to make sure that is correct, which it is. Okay, so we've now got that, and I'll write it underneath. That is in completed square form. So hopefully you're quite useful now you're finding it quite helpful, and you're quite used to putting something in completed square form. So when we've done that, we now are being asked to find the greatest fuel efficiency, okay? And the speed at which that greatest fuel efficiency happens. Well, that's the greatest fuel efficiency. We can take the turning points. We can say the turning point is at 195 over 4, and, well, 2545 over 64, and it might be quite useful to write those as decimals. So if you write those as decimals, it's 48.75. And if I just put that into a calculator, it's 39.765 ... And remember, those coordinates are x and y coordinates. And x in this case is speed and y is fuel consumption. And again, if we look at our quadratic, we've got a negative coefficient of x squared. Our x squared term is negative. So just like the other example, we're going to have that shape of our quadratic. And so our turning point is up here. The turning point is a maximum in this case. And so we can just read off the turning point. And so the maximum fuel consumption, or is it fuel efficiency? The greatest fuel efficiency or consumption in the question. The maximum fuel consumption is 39.765, and that is at time of, is it time? Oh no, sorry, that is at speed of 48.75 miles per hour. Okay, and so that is your final answer. We'll highlight all of that in yellow. That's what we needed to do. So hopefully that makes a little more sense. There's tons of questions online and in textbooks to have a look at different examples, but those were just 2 examples of modelling with quadratics.